Our next video here is about velocity of sound in air. And it turns out that the velocity of sound in air changes with temperature. When the temperature goes up, molecules move faster, pressure goes up. When pressure goes up, the messaging of the wave goes much quicker. So the response time of the wave to the air goes quicker, so sound waves start moving faster through the air. The equation here is that this is the speed of sound at 0 degrees centigrade, or the freezing point of water. This is 273 degrees Kelvin, which is the freezing point of temperature in Kelvin degrees. And of course, this is the temperature in Kelvin. So we have to convert to Kelvin to use that equation. So let's say at room temperature, which is about 20 degrees centigrade, which is 293 Kelvin. We just add 20 to 273 to get 293. We can then calculate the speed of sound in air at that temperature. So V, when the temperature is equal to 20 degrees centigrade, is equal to 331 meters per second times the square root of 293. Whoop, there we go. 3 divided by 273 minus 1. And let's see what that is equal to. So 293 divided by 273 equals, subtract 1 from that. Oh, wait a minute. We don't need to subtract 1 from that. That is just fine. Don't subtract 1. Just leave it like that. That's the proper equation. Sorry about that. Proper equation is this. And then we take the square root of that. And then we multiply that times 331 equals, and we get 300. Oh, let me try it again. I didn't do that right. 293 divided by 273 equals, take the square root, multiply it times 331, and we get 343 meters per second. So at room temperature, the speed of sound is 343 meters per second, which is approximately equal to 1,100 feet per second, which is approximately equal to 1/5 of a mile per second. Now there's an interesting fact, because what that means is if you see lightning strike about a mile away, it'll be about 5 seconds, because it takes 5 seconds for sound to travel a mile before you hear the rumble of the thunder of that lightning strike. If lightning is 2 miles away, it will take 10 seconds and so forth. So there's quite a bit of lag delay in the sound reaching you if the sound was made a long distance away from us. Let's figure out what the speed of sound will be at 100 degrees centigrade. So the velocity of the temperature in the air when it's 100 degrees centigrade, that's equal to 331 meters per second, multiplied times the square root of 100 plus 273 is 373. That's the 100 degrees centigrade in Kelvin. Divide by 273 and see what we get there. So we have 373 divided by 273 equals, and then we take the square root of that, and we multiply that times 331, and we get 387 meters per second. So this is equal to 387 meters per second. Now, this is kind of interesting also for pilots, because most planes are not made to break the speed barrier. And the speed barrier is around 700 miles per hour at temperatures that are like room temperature. So let's see here. Let's convert. Let's get a good picture. So we have 343 meters per second. So 343. If we divide that by 1.609 and multiply times 3,600, we get, and then divide by 1,000, we get 767 miles per hour. So this is equal to 767 miles per hour. And most jets are not made to fly that fast, so they don't have to worry about the speed barrier, to break the speed barrier. If a plane is not made to break the speed barrier, it better not try, because they'll probably break apart, or the pilot will have a lot of problems controlling the aircraft. But way up there where the air is much cooler, sometimes as much as minus 50 C, what is the speed barrier what is the speed of sound at that point? So the velocity when the temperature is about minus 50 C, what is that equal to? Well, let's try find out. 331 meters per second times the square root of, subtract 50 from 273, we get 223 over 273. And let's find out what that is equal to. So 223 divided by 273 equals, take the square root of that, multiply times 331, and you get a speed of 299 meters per second. And if you convert that to miles per hour, let's see what we get. So we have to divide by 1609, multiply times 3.6, and we get 669 miles per hour. So notice that most planes, most passenger aircraft, they don't fly at that speed. They need to stay well below that speed, because if you get anywhere near it, things are going to start drastically wrong. So passenger planes that fly at 30, 35,000 feet, that encounter temperatures that are easily that cold, minus 50 degrees centigrade, they better stay well below this speed or they're in trouble. So speed of sound is important and something that we need to consider. And that's it.